Hello, and welcome to this presentation titled Transforming Fake News, Robust Generalizable News Classification Using Transformers, where we'll be talking about investigating the role of transformers in news classification. So, first of all, what are we talking about when we talk about fake news? Now, fake news is actually a very difficult term to define because it's very, very broad and has become a bit of a catch-all term since it was first coined during the 2016 US presidential election. But the general definition that we'll be accepting for this presentation is that fake news is a news article that is intentionally and verifiably false. So, what then is the fake news problem? Well, the problem with this fake news is that it generally appears online because there are not the same editorial standards when you post a news article online compared to when you publish a printed newspaper, for example. So while this is a really great thing that there is so much more information available and easily accessible to really wide ranges of people online now, it does also mean that it's much harder to find out whether what you're reading is real or fake. And as we can see, there's been quite a sharp increase in the percentage of UK adults who use the internet for news from 2016 to 2020. So what this really shows is that more people are accessing their news online. So it's becoming more and more important to be able to find out whether what you're reading is real or fake. So there are three main approaches that have been suggested to date to solve the fake news problem and to identify news and classify it as real or fake. The first of these being a content-based approach. And so content-based approaches consider solely the text of a news article. They look solely at the words used, the grammar, style of language, and take all of that into consideration to classify news as real or fake. The next approach is a social context-based approach. So this takes into consideration the fact that news online doesn't exist in a vacuum and it can be engaged with. People can share news articles, they can comment, they can like, they can dislike. There is a whole range of ways that people can interact with that news article, and all of that then becomes social context that can be used as extra information to try and classify that news article as real or fake. And then the third and final approach is a hybrid approach combining both the content-based and the social context-based approaches. And the approach that we have taken for this study in investigating how transformers perform in identifying news as real or fake is a content-based approach, with the reason for this being that this allows for the earliest identification of news as real or fake, because when including social context, while the extra information may prove helpful in classifying news as real or fake, it only partially solves the fake news problem because it means that you can only classify news at the point that it's already been posted, read, shared, and engaged with. So a content-based approach really allows for the earliest classification, and so this is the approach that we have taken. So when looking solely at text, the reason we have chosen to investigate transformers is because they have really reached state-of-the-art capabilities in a wide range of natural language processing tasks, from machine translation, summarization, and also to classification. And they do this largely by relying solely on attention and self-attention mechanisms, which allow transformers to avoid the informational bottleneck of other approaches, where you're trying to encode huge amounts of information into one final vector. With attention, you're able to direct your model to look at specific parts of a sentence that contain the most relevant information to make a prediction. So what differentiates BERT-based models from the traditional original transformer architecture is that they are able to get a bidirectional understanding of text. So BERT stands for bidirectional encoded representation from transformers. And the way that BERT-based models are able to do this is through masked language modeling, which makes up the first step of their unsupervised pre-training. So masked language modeling, what happens in this process is input tokens are randomly masked and then they are predicted. So this means that the model can learn both right to left and left to right, because without this, trying to learn backwards would be a trivial task in that the model would already know the word that was there, and so it wouldn't be able to learn anything going backwards. So this allows for that bidirectional understanding. And then the second part of this unsupervised pre-training process is next sentence prediction, where sentence A precedes sentence B 50% of the time, and this allows the model to learn the relationship between two sentences. So the first model that we'll be considering is the original BERT architecture. We'll also be looking at Distill BERT, which is, from the name, a distilled, more compact version of BERT that contains very much the same level of understanding, but it's computationally much less expensive, much quicker, and it's much less computationally expensive. And then we'll also be looking finally at DBERTA, which stands for Decoding Enhanced BERT with Disentangled Attention, and this builds on the original BERT architecture, trying to build in embeddings for more context of words. So transformers are obviously deep learning models, which means they need a lot of data. And so the two data sets that we've identified as being suitable for this study are the ISOT and combined corpus datasets, which have around just under 40,000 and 80,000 rows respectively. And we can see that the datasets are relatively balanced with some minor imbalances towards different classes. And if we investigate the topics that are combined within these datasets, we can see that they're actually really quite different in scope. So looking at a word cloud of the most frequent words that come up in the ISOT dataset, it's quite obvious that this dataset is very much focused on US politics, and in particular on the 2016 presidential election, with the largest words being Donald Trump, and then we can also see White House, Hillary Clinton, United States, government. So the scope of this dataset is quite clearly focused around US politics. But if we then look at the word cloud for the combined corpus dataset, the largest and therefore the most frequent words are much more vague, much more broad, don't necessarily tie themselves to a specific topic. So one, time, said, say, even. These are very broad words. So what we can see is that the topic distributions between these two data sets are really quite different, with one being very focused around a particular topic, US politics, and the other being much broader in scope. So the proposed approach to investigate how transformers perform in classifying news as real or fake is using solely textual content. We'll compare the three BERT-based transformers to baseline machine learning and deep learning models for news classification as real or fake. So we can see in the left column the baseline models with logistic regression, naive Bayes, and random forest forming the machine learning comparisons, with LSTM, long short-term memory, forming the deep learning comparison, and then we have our three BERT-based transformers. So in order to test all of these models and their performance on this classification task, we will first of all test in distribution generalization, so testing how they perform when trained and then tested on a holdout test set from the same data set, so with similar class distributions with similar topics. Then number two, we'll test out of distribution generalization, so testing how do these models perform when they're trained on one data set and then tested on the other, which will have completely different class distributions, topic distributions, potentially writing styles. How are these models able to generalize? And then finally, we go on to propose a two-step classification pipeline to try to mitigate some of the unique challenges when trying to classify news as real or fake. So what are the challenges in identifying fake news? Well, if we go back to our original definition, that fake news is a news article that is intentionally and verifiably false, that raises the question of what about opinions? It's very difficult to say whether someone's, or potentially impossible to say, whether someone's opinion is right or wrong, true or false. And I'd just like to point out an interesting example of this with the viral dress that hopefully many of you have seen before. This image went viral a good few years ago now, because people couldn't decide what the colour of this dress was, because everybody had their own interpretation of what colour it is. So for me, on looking at this dress on my screen right now, this is blue and black. And hopefully it will not be blue and black to all of you. Hopefully there's someone looking at their screen right now screaming at me saying, it's obviously not blue and black, it's white and gold or blue and gold. I think they are some of the other options that people can see. And so the point of this is to say that I'm not right for seeing this dress as blue and black. And if you're seeing it as white and gold, you're not wrong. We're simply interpreting this image in different ways and coming to a different conclusion when presented with the same information. And that is to say that when people are presented with the facts of a situation, they can come away with two very different opinions. And it's incredibly difficult, if not impossible, to say which one is right or wrong, and to say whether something is intentionally and verifiably false when talking about an opinion is very difficult. Another challenge in identifying fake news is looking at sensationalized language. Now, it seems that sensationalized language is more commonly associated with fake news compared to real news. So these are two headlines taken from the data sets that were labeled as fake. So they have sensationalized language such as crumbling, shocking, you won't believe. But headline taken from the data that was marked as real contains the words shockingly weak, that to me also sound quite sensationalized. And when looking at quotes that are included in headlines or in text, those quotes, if they are taken verbatim, they could be incredibly opinionated, emotional, sensationalized, and that doesn't necessarily mean that a news article is fake, because the language in it is very strong and very sensationalized. So how can we mitigate for this to make sure that any model that we train doesn't simply learn that sensationalized language equals fake news, when that's not the case, and opinions can often use much more sensationalized language? So how can we mitigate for these challenges? So the solution, a potential solution that we propose, is this two-step classification pipeline. So in this pipeline, we have two classifiers, the first of which being a fact versus opinion classifier, then followed by the actual fake news classifier. So how this works is you take your input passage, so you take your news article. This is then passed to the initial fact versus opinion classifier, which outputs predictions as to whether news articles are fact-based or opinion-based. And only those news articles that are fact-based then go on to form the training data for our fake news classifier, which then outputs the final predictions for fake news and for real news. So by filtering out those opinion-based news articles, we're filtering out news articles where it's potentially impossible to actually say whether they are real or fake, and how they've been labelled in training data that we found in open source data sets. If they are opinion based, those labels are incredibly difficult to actually say whether they're right or wrong, and could be incredibly subjective, meaning that there could be patterns in that labeled data that are very subjective, unique to the one fact checker who said that this news article is real or fake. And so these could lead to our models learning spurious or incorrect patterns within data. So by taking them out, we try to mitigate for that and try to find patterns that do generalize well. So for the fact versus opinion classifier, we've manually created a data set, a very small data set of only 50 rows. So there is a lot of scope here for further work for news articles that have been manually labeled as opinion-based and fact-based. And then we've trained a Dilbert model on this data, which reached a 78% accuracy, and this formed the fact versus opinion classifier for our two-step classification pipeline. So if we go on to look at the results of this study, when looking first at in-distribution generalization, we can see that overall, all of the models performed very well. But we can see that the three BERT-based models outperformed their counterparts across every metric, with the Dilbert model performing the strongest across accuracy, precision, recall, and F1 for both datasets. So this model performed very strongly. When we then move on to look at out-of-distribution generalization, it's clear that there is a big drop in performance across all model types. But this is to be expected because these models are now having to generalize on a data set that is quite different in topic distribution, class distributions. So for out-of-distribution generalization, models were trained on one data set and then tested on the other. And as we've seen, the topics that are covered within these data sets are really quite different. So it is quite a challenging task. So it does make sense that there is a drop in performance. But highlighted in bold is the highest score across each evaluation metric. And we can see that it is across all metrics, it is the BERT-based models that do perform the best. So they are still performing very strongly on this out-of-distribution generalization task. However, if we delve into these results a little bit deeper and see how these BERT-based transformer models are actually performing for each class, we can actually see that some of these evaluation metrics drop below 0.5, indicating that they actually perform worse than random chance in predicting whether a news article is fake. So this is looking at the positive class where they are below 0.5. So what this potentially indicates is that these models are actually learning incorrect patterns that make them worse than chance, worse than random choice at identifying fake news articles. So this confusion matrix shows the results for a DeBerta model trained on the combined corpus dataset, and this is without removing opinion-based articles. So this is without the two-step classification pipeline. And it's quite clear that there is a really high proportion of false negative predictions and quite a low proportion of true positive predictions, showing that this model is very much skewed to predicting that news articles are real, because negative predictions are real in this case. So if we then look at the confusion matrix for the same model with opinion-based articles being removed and the two-step classification pipeline being implemented, we can see that there is quite a smaller proportion of false negatives and a larger proportion of true positives. So this indicates that by removing those opinion-based articles, our model has been able to learn more generalizable patterns that have allowed it to perform much better for this out-of-distribution generalization task. So to look at a quick summary, we can see that the BERT-based models achieve the highest performance across all tasks, achieving the highest performance metrics for both in-distribution generalization and out-of-distribution generalization. And when we went on to investigate removing opinion-based articles with the two-step classification pipeline, this did seem to allow for better generalization to unseen data, with there being a much larger proportion of true positives, a much smaller proportion of false negatives. So looking at future work, there is a lot of scope for further development of our fact versus opinion dataset to investigate this further, to investigate the two-step classification pipeline further, to find out really what is the effect of opinions on this task. There's also room for some really interesting work in including information from image data accompanying news articles in classifying them as real or fake. Because when you're looking at online news data, it's very often accompanied by images. So this could be something really interesting to look at for future work in this topic. Fake news classification is a really important topic. It's becoming more and more important, as we've mentioned, that more and more people access their news content online. So I really hope you found this presentation interesting, hopefully giving you something to think about. And yeah, thank you very much for your attention. I'll be really happy to answer any questions that anyone may have. Thank you so much.